This is problem 126 from chapter 12. It uses the same figure as problem 125. The car travels around the portion of a circular track having a radius of 500 feet, which is different than what it was in problem 125, such that when it is at point A, it has a velocity of 2 feet per second, which is increasing at a rate of 0.002 t. Determine the magnitude of the velocity and acceleration when it has traveled 3/4 of the way around the track. Okay, so this has different numbers than problem 125, but you basically solve the problem the same way. So you have v dot, and you can find the arc length, then you can integrate and keep the upper limits of integration symbolic just like we did in the previous problem, then integrate again, and now you can plug in s at point B, and we're going to find the time at point B, and then you can solve just like we did in the other problem using a solver. So use a computer, the other solutions are imaginary, and then put this time into your velocity equation to find the velocity at point B, and then for v dot, do the same thing, put this time back into this equation for v dot, and you get v dot at time B, and then look at the acceleration vector and put in the values that you have at point B to find the acceleration at point B. However, so that was pretty much the same as 125. The answer in the back of the book is for when v dot is equal to 0.002 s, not 0.002 t, which I think would be much more interesting to look at because otherwise it's not really that much different than 125. So let's look at what we would do if instead we have v dot is 0.002 s, which is not what they told us in the problem, but it makes things more interesting and it gives us the answer in the back of the book. So if instead we have v dot as a function of s, rather than having dv dt and integrating that, we're going to, since it's a function of position, use equation 1219. So that's what I have here, and now we're going to integrate that starting at when the velocity is, what did I do there? I think we want to say starting when the velocity is equal to 2. So that should be a 2. Whoops. If the position, if we're going to say at A, that's when s is equal to 0. So we integrate both sides, and you can pull out the 0.002, integrate s ds, you get 1/2 s squared, so dividing the 0.002 by 2, you get 0.001. Putting in the lower limit of integration just gives you 0. On the other hand, on the other side, when you integrate, you have 1/2 v squared. Now when you put in the lower limit of integration, because it's 2, you get 2 when you plug things in. Okay, we still want to find the distance that the car travels as it goes from A to B, and we can get that from the arc length formula, just like we did in the previous problem. We take the radius and we multiply it by, when you go from here to here, that angle would be 3 pi divided by 2, and that gives you 2,356. Okay, so we want the velocity at point B, and that's going to come from our equation here. If you solve this for the velocity and then plug in s, that would be here, you get 105.4 feet per second. You can fill in the missing steps for that. And then we also want to find the magnitude of the acceleration, so we have our acceleration vector here. I have v dot here. I take the value that I have for s at point B and plug that in here. That gets me v dot. That's 4.712. Then I have v squared divided by rho. Here's my v, so I square that, I divide it by the radius of 500 meters, and then to find the magnitude of the acceleration, I square each of these, add them together, take the square root, and I get 22.7 feet per second squared. So that's how we would do it if we have v dot as a function of s instead of as a function of t, and this should agree with the answers that are given in the book.